All right, everyone. Welcome. We are going to be talking about using the Kotlin language for advancing development on Android, advancing how we develop apps. So to start with, we need to figure out why do we actually need to move Android development forward? Why do we need something that's advancing development? A classical reason that a lot of people make is that we're stuck in this Java 6-ish, almost Java 7. It's been called a wasteland. So we have Java Xtime is a library that came in Java 8, JSR 3.10. And so we don't have this on Android. We're stuck with the old date APIs and calendar APIs, which are fraught with problems. There's no streams, another Java 8 feature. The language features, so lambdas, method references, and anonymous classes that don't capture a reference to the outer class. And then finally, try with resources. And so try with resources is actually in Java 7, and Android went to almost Java 7 in API 19 with a little bit more in 20, but not all the way. So only if you have a minimum SDK can you use that. But as it turns out, even though these four things are really painful, these aren't true. So for Java Xtime, there's the guy that wrote the majority of the code for Java 8 for the JDK actually backported the library to Java 6. And so you can use that, you can bundle that in your app. For streams, there's also a backport that takes it back to Java 6, or a popular Java library, RxJava, basically implements the same concept in a slightly different and arguably more powerful way. There's a tool called RetroLambda, which will actually take Java 8 bytecode and backport these lambdas and method references back to Java 6. And like I said, try with resources if your min SDK is 19, but RetroLambda actually will also take try with resources and backport it to work on Java 6. So these arguments that people make about Java 6 being a problem, there are tools for that. I mean, granted, it would be nice if we could just Java 8 out of the box, but these workarounds are fairly well battle tested and certainly are available in work. So that one doesn't really count. But there's two that I really want to focus on which can't be fixed in the same way. And it's just restrictions in the Java language and the problems that it presents. So we have this inability to add methods to types, to classes or interfaces that we didn't write ourselves, that don't exist inside our project. Traditionally, these wind up in util classes, just littered all over your code base or slammed together in one util package. And so while this is a solution, it's certainly not ideal. The type system in Java, and especially in using it on Android, has problems with null. It has no first-class representation of types that may be null or may not be null. And so oftentimes the so-called billion-dollar mistake of the null pointer exception ends up killing your app. And then just, Java is certainly not the most terse language, and that's not necessarily a bad thing, but there's a lot of common idioms that just end up being overly verbose, which can potentially lead to errors and bugs in your code. So that's the Java problems with the Java language itself, and there's also the Android API that we have to deal with. So Android is a big inheritance party. They love their inheritance, which works well for them, but it tends to push problems on us as application developers. The nullability problem comes back, and this is especially apparent in Android where they want things to be efficient. So null is used in a lot of places to represent the absence of a value instead of something that would wrap it at a more high level type, which, kind of like an either type or optional. And then, again, back to the verbosity, Android itself, its APIs have a lot of ceremony, and this also goes back to just wanting to have high performance, is that they end up writing these APIs that require you, the developer, to do a lot of things in order to provide efficiency instead of abstracting it all away. So Java and the Java language and the Android APIs are really the two motivating factors for why something like a language like Kotlin could be appealing. And it's not to say that the Java 6 stuff isn't a problem, because Kotlin addresses a lot of that stuff, but I don't think it's a good enough argument to make because of those alternate tools. So if you don't know Kotlin, Kotlin is a language by the company JetBrains, developers of IDEs for tons of different languages, the IntelliJ platform, which is the basis for Android Studio. And so this is their little website. It's a statically typed language for the JVM, Android, and actually the browser as well. So it will compile to JavaScript, although that focus has been pushed back beyond version 1.0. But it's really targeting the JVM and Android and Java 6 bytecodes. They want to add these new features in the language while still supporting these markets of the Java 6 and up, JVM, and obviously Android. And they focus heavily on interop with Java, so we'll see that a little bit later on. All right, I'm not going to cover a ton of introduction to Kotlin, the language, and the syntax itself. The website and the tutorials are really great for going through this, but I didn't want to kind of just jump into why the language is good for Android without going through some syntax that we'll see. And while I'm not going to cover everything, there will be points throughout the rest of the talk where I'll introduce some new syntactical elements. So to start with, this is what a method looks like. We have a fun declaration, which stands for function, the name of the method, and the first thing to note that's significantly different than Java is that the order of the argument name and the argument type is reversed, so the type comes after the name. The return type is specified on the end of the method. And actually, and there's no semicolons. So you'll see the return does not have a semicolon after it. And what's also interesting is that because this is a single expression function, the function body only has one expression inside of it, we can actually get rid of the curly braces and the return and actually just make the method equivalent to the expression. We'll see this shortened syntax comes in really handy later on. Here's another example. This would be what a main method looks like if you're writing just a normal Java application. We see that there's the array syntax for a type is a little bit different. It's treated more like a generic. The bytecode that gets emitted will use a string array, but in your code, you get to treat it like it's just a generic array. And then while we're not going to touch on this pretty much anywhere in the rest of the talk, there is string interpolation. So we can write strings and reference variables inside of them and have it be automatically replaced. And finally, just a look at some variables. So here I'm assigning a string to a variable called name, and there's no type here. It's actually going to infer the type because it can only be a string. And you'll see that it's prefixed with val. Val is a value, which is an immutable type. It can't be changed. And if it were something that was mutable and we wanted to change it, we would use var for variable. So here's what a type looks like on a field. It comes after the name, just like in a method. And then finally, when we call constructors, we actually don't have to use the new keyword. It's the exact same syntax for the rest of it, but just dropping the new. Okay. Let's move on into the features of the language and how they're going to help us in building our Android apps. So I pointed out that these util classes are they're not necessarily a problem, but they're almost kind of an anti-pattern, and they end up growing out of control in your application. So Kotlin has this concept called extension functions, and it's not unique to the Kotlin language, but it ends up working out in a slightly different way than we see in other languages. So if we wanted to add a method to date in just pure Java, we would write a dateUtils class or dates class and put a static method on it, and that just takes in an instance and does something, potentially returning a value. So here I'm adding the ever useful isTuesday method to our dateUtils, and then we would just call it as a traditional static method. So Before I show the Kotlin syntax, I want to contrast this with C#. This is what an extension method would look like in C# on its version of the date class, datetime. And so the interesting thing here is that we get our date instance and we can call this method, and this actually works anywhere in your entire project in .NET. So as long as there's an extension method declared somewhere, you can use that on any date time in the entire project. And I'll explain why that's an interesting distinction in a second here. All right, so here's Kotlin. We prefix the method name with the type that we want to add the method to. So instead of just isTuesday, we're now date.isTuesday. And then you can see our return type at the end, and we end up calling getDay. And so this extension function is acting as if it was on the type, so we don't have any instance to call. We just call as if we were already a method on that class. Okay, and then, yeah, this is how we would call it. So now if we have a variable in that same file, our date objects would now have an isTuesday method, and you would call that like any other method on date. One of the nice language features of Kotlin is that it actually automatically will convert types that have getters and setters to have synthetic properties. So I'm no longer calling getDay. I'm referring to this day property which exists. And so this doesn't, it kind of looks like a field, like if this was a public field, but it's not. This is a property, and so a property is just the concept of a getter and a setter merged together. And I pointed out earlier that single expression methods can be put into a more terse syntax, so we can actually just move that up into the top and get rid of the return type because it can be inferred, and now we have this nice little one-line extension method that we can use on date. Now, when I said we're calling this on like a field in the same file, that was something that's important, and that's why it's different than C#. So if this is in the same file, this is going to work. However, if our extension method is defined in some date extensions class, and our field that we're using it on is in, say, some activity, this is actually not going to work. You will get like a method not found indicator. It'll be nice and red in Android Studio. And that's because, unlike C#, extension methods have to be explicitly imported if they're not in the same package. So here we would have to be very explicit about where this extension function is coming from. And so this is very similar to how Java already works with its static method imports. We have to be very explicit about the method that we're calling, and this allows it to be unambiguous about the source of that method. Because if I look at this, I know there's no isTuesday method on date as a Java developer, but the explicitness of the import tells me that it's coming from this com example util package, whereas in C#, you have no idea where that extension method is coming from. It might be a library, it might be in your source. You have no way of knowing statically without actually going into the IDE and allowing it to figure it out. And of course, like you can command B and step into this method. It behaves just like it was a method on the date type. So let's see. This basically is what the bytecode is going to look like when the Kotlin compiler runs, because obviously this has to turn into Java code, right? Like there's no Kotlin runtime that's running on our devices or on the JVM. It's just running on the normal bytecode interpreter. So if you haven't seen bytecode, this is the Java equivalent of what that bytecode represents. And you'll notice it is exactly the same thing as what we would have otherwise wrote if we only were doing Java. It's that same static method. An interesting thing is that if I mentioned that Kotlin wants to interop with Java, it understands that your entire project can't be Kotlin code. So this actually is going to wind up getting generated in a class called dateExtensions.kt.java. And that's because the class that we've defined it in is called dateExtensions. And so if we were interoping with existing Java code, we would want to present this as if it was something written in Kotlin. You shouldn't know that you're calling into Kotlin. It has a handy annotation that you can put on the file, which allows you to control the generated name. So in this case, we want to turn it into dateUtils so that it looks like our old dateUtils class. And of course, you don't have to continue with the utils naming convention. You can use whatever you want. The point is that you have the ability to control it. And also, just remember that this dateUtils.java class the class exists, but the source file doesn't exist. So this is just a representation of the class file that gets generated. Now I'm going to have to speed up the rest of my talk. One thing that you can't do, you cannot override an existing method. So if a class has, like our date class has getDay, we can't actually override an existing method. That would create some ambiguity. But it's actually slightly unfortunate because this would be a fantastic way to retrofit APIs that are on newer versions of Android to older versions of Android. We could conditionally call into the real method if it was available, or fall back to a compatibility version if we're on an older version of Android. So that doesn't work. So you could do something like add a compat version directly on the class that you wanted to, instead of having to do like view compat and all that stuff. So a really good use for extension functions is taking an existing API and fixing how it's broken. So text view has these two awful methods, and you're almost always going to call them incorrectly. The first one doesn't really specify what units it's in, and the second one has its parameters out of order. It doesn't really make sense to say, I want to set the text size to pixels 6. Traditionally, you put the unit after the size. And so this is a great way that we can just slap a new method onto text view that's much more semantically correct, that takes a size, and then we can actually enforce some kind of, dare I say, enum to use the units, and then that enum can have behavior which converts it into pixels, the value into pixels, and then we just call into the normal set text size method. And so it is impossible to call this method incorrectly, because you have the number, which can only be a float and represent what size it is, and you have the enum, which stands for the what unit the number is actually representing, and it takes care of converting it to pixels itself. Another example is Cursor. Cursor is one of these classes that's really optimized for, its APIs are optimized for being efficient, not exactly for being useful. So in order to get a string for a column out of a cursor, we have to make two method calls. We have to get the index of the column that we want, and then get the string at that index. And so if this column is nullable, we have to do a lot more than that, because we have to get the column index, then we have to check if that index is null, and then we can conditionally get out the string. This is terrible code to have to write every time you want to get something out of a column. Or a cursor. Sure, you could wrap it in, our static util method, but that's exactly what these extension functions are for. So we could add two methods to the cursor type, which is going to take care of doing this dance for us, where all you now have to do is pass in the column, and it will take care of doing the conditional reverse looking up the index. So an interesting thing here, let me move it up. Interesting thing to note here that I haven't covered, I talked about nullability being a problem. Kotlin actually represents null in its type system. So for the getString or null method, I'm returning a string question mark to indicate that this might return a null value. And then down in the getString method, I'm just calling the or null and using this double exclamation mark syntax. And this is basically just saying, I know this is not going to be null, so turn it into just a normal string. And so this will actually emit a check where if it is null, it will throw an exception. But in the consuming code, the code that's calling this method, the type will be a string question mark. That will be propagated, if you're calling the first method, that will be propagated down to the calling code. And that means that you can never dereference that field without first doing a null check or providing a default. So it virtually eliminates the ability for this to cause a null pointer exception in the code that's consuming it. All right, the next concept we're going to look at is called function expressions. And elsewhere, these are known as just lambdas or maybe closures. So here's an example of the simplest version of a function expression. It's basically just a block of code that is calling the toString method on this it variable. And so it is actually a built-in name when you're writing these function expressions. If there's only one argument being passed into this block of code, you can refer to it as it, and it's just a way to not have to define arguments. But if we do need to define arguments, or there's more than just one, this would be the syntax for doing that. So we can create a piece of code, a function expression, which takes in two pieces of data and adds them together. If we want, we can specify explicit types. For the second entry there, we could only do that if the types were somehow inferred from some other context. But if we need to declare explicit types, we would do the same, placing it after the argument name. And then, like, to store these in fields, so now you can see that the second example, rather, the type is declared on the field itself, which means that the function expression doesn't need to include any type information. And then down at the bottom, the type information is included in the function expression itself, so we don't need to include it in the variable declaration. And also in the last one, the return type is inferred. So it knows that two integers are going in, and it knows that it's adding them together, and the only thing that can come out is an integer, so you don't have to be explicit about it. Just an example of like how these are useful. We're going to look at these a lot more. I just need to introduce the concept first. So if we wanted like validate data that's coming in, we could check if a string's not empty or if its length is greater than 4, et cetera, et cetera. So here's storing them as fields, and the idea here is that chunks of code now become data that you can move around. So I can declare this piece of data, this data that operates on a string and does validation, and I can have it in a field or a variable and then move that around to the place where it's needed. We'll see where this comes in handy later. All right, so the next thing is higher order functions, and this is just a really fancy term for functions that accept a function or functions that return a function. Here's an example. So we define a function which is going to take in two integers, and then as its third argument, it's actually going to take in a function. So that's the same syntax that we saw on the previous slide, where we're defining a function that takes two integers and returns an integer. And then inside the method body, it's just going to call that function with the two parameters. So here's how we would use it to create a sum. We're applying this block of code onto these two numbers. And we could also use that to get a difference. So we apply a different block of code to those two numbers. And again, this goes back to the point where we're taking this code that knows how to add, or this code that knows how to subtract, and we're turning that into data that we can pass into this apply method, and then it can take care of running it when it has the appropriate context to run it. And so Kotlin actually gives you a handy way of turning this into a slightly nicer syntax, whereas if the last argument of a method is an expression, you don't have to have the parentheses all the way at the end. You can just have it after all the initial arguments. So the parentheses at the end here, we can actually just slide over before the function expression and add the function expression at the end. And it's still calling that same method, but now we've made it, the syntax is a little more nice. And we'll see that this technique is going to allow us to create really nice like DSLs and APIs later on. Okay, so right now I'm taking in two integers. These high order function could also be just an extension method. So instead of taking in two integers, I'm now making an extension method on an integer. And that would change the calling code to look like this. So our integers now have methods that we can apply some behavior to another integer. I know the syntax is going to come in use later on. I know the examples are kind of weird. The ones at the end will really resonate, though. And so you also don't have to take in any just normal arguments. You can only take in the function expression. And what's nice here is you don't even have to specify parentheses at all. So now we're applying some block of code onto a number. Also a really weird example, but you'll see later that this syntax is now going to create something Very powerful. And again, if there's only one piece of data being passed to a function expression, we can just refer to it as it. All right, so let's take a look at some more practical applications of how this would work. A common operation is just having a list of things and needing to filter it based on some condition. So now we can, because we have extension methods and because we have high-order functions, we can write this. We can write a method on list that does this for us. And we would do it in the normal way. Sorry, we can look at just the syntax here. So it's just an extension method, and it's taking in an expression which uses the generic type and returns a Boolean. So we'll just call this for every item in the list and then return a new list that only has the items that return true. And it's exactly the same as you would do if you were doing this manually. You create a new list, you loop over the items in the list, you call some function or some inline the if statement, and then if it returns true, then you add the method or you add the instance to the new list, and at the end, you end up returning it. And so now if we have some list of data in one line of code in this nice terse little function, we can now filter it to only pull out the things that we need. Thankfully, this function is actually built into the Kotlin standard library, so we don't actually have to extend lists. A large majority of the standard library of Kotlin is just augmenting these Java types that already exist with these higher level methods that provide common operations on them. An example that doesn't exist in the Kotlin standard library, we could add a method, instead of doing synchronized blocks, we could use an expression to execute code in a synchronized block. So any is Kotlin's version of object. Every type is a subtype of any. And we can add a method to it that just takes in a function and executes it inside a block that's synchronized on that instance. So if we have some lock or some object that we need to lock on, we can put the code that executes inside that lock inside a function and pass that to this method that's on every instance. And so it cleans up the calling code and makes it a little bit more clear. And another pretty cool application of this is that a common problem with doing locking is that oftentimes you'll have code that forgets to do a lock before it does some operation. We can write a class that actually only allows you to access the type that you need to interact with if you have a lock on it. So it's impossible. In this case, we're creating this JSON reader, which is on some stream, and say we're accessing it from multiple threads. Not that I know why you would be accessing a JSON reader from multiple threads, but this is going to prevent us from accessing this instance unless we take this lock, which is going to take care of synchronizing for us. So later on in the code, we call this acquire method, and it's going to synchronize on that instance and then pass it to the function that we gave it. And so in this case, I read a string from this JSON reader, and we can only do that if we have the lock. And so now here, we're not dealing with locks at all. We're not dealing with the explicit synchronization and having a lock and the JSON reader. It's impossible for us to access that JSON reader without taking the lock. Solving bugs, preventing bugs before they even happen. And so earlier on, I talked about the code as data. And so here was our code. And so we could now, with this high order functions, we know how to use that. So we could have a method on text view that does the validation for us. And then we can pass these functions into that method and allow it to do validation as someone's editing and edit text. An interesting thing to note is that the way that Kotlin implements these pieces of code in a function expression is the same way that you would do it in Java. It uses classes. And so what's nice is that it's not actually, normally you would do like validate with, and you create a new anonymous class and put your data in there. But that's actually, when I talked about non-capturing anonymous classes, that class that you create is going to have a reference to the outer class. And so that's a great way to leak a context, and that's not what we want to do. But Kotlin, when it creates this class, because there's no reference to the outer scope at all we care about is the data being passed in, it's going to create a singleton instance that's static and has no reference to the instance at all. So it's now impossible to leak a context with these function expressions. But at the very top here, we have two that are the same. It's actually not smart enough, and it could be argued as not even being correct, to deduplicate. So even though they're exactly the same pieces of code, they're going to turn into two generated classes, each of which have their own instance. So if you wanted to eliminate that, you would just have to deduplicate it yourself. Store it in a field first, or store it in a variable, and then pass that in. Okay, so this is where we've been getting to. We talked about extension functions. We're adding methods to types and allowing them to behave like those methods were always there, that they're natural to that type. We talked about representing code as data, just these function expressions that we can pass into methods. And then the high order functions, which is the fancy name for a function that takes a function. So extension function expressions are the combination of all three of these concepts into a really powerful way to make clean APIs. And so to demonstrate that, I'm going to take an API that we're back to databases. I'm going to take this API and turn it into something much more terse and prevents us from writing invalid code. So these are the 6 lines of code that you would have to write if you wanted to execute a statement in a transaction. We start the transaction, we put it in a try finally, we execute our code, then we have to mark the transaction as successful, and if that throws or it doesn't throw in the finally block, we have to end the transaction. This is the type of code that's prone to bugs, to forgetfulness, to refactors. Anything could go wrong here where you accidentally swap two things, and all of a sudden you have a very subtle bug that's hard to catch. Or maybe it just blows up all the time at runtime. And so extension function expressions are going to allow us to fix that. So we can now add a method to the database itself, which is going to encapsulate the boilerplate of that chunk of code, the starting the transaction, the doing the try block, and setting the transaction successful, and finally ending it. And so we take in a function, and we run that function inside the try block after we've done that little dance. And now in our consuming code, we just have this method that we call inTransaction on, and anything we put inside that is going to execute inside a transaction. There's no way for you to screw this up. Almost no way. An interesting thing here is, so the way that we've implemented this, you still have to reference the database inside the piece of code. And so that could potentially be something that you mess up. If you have two databases, maybe you reference the wrong one inside a transaction for the other one. And so we have ways to fix this. One way we could do is we could actually take in a function whose arguments takes in the database that the transaction is on. And now instead of calling DB, so we have to pass in this into the function. And then now instead of calling DB, we can just use that first argument that's passed to the expression. So this is still kind of annoying. We've potentially prevented a bug, but it's still annoying to have to specify it every single time you want to access this database. And so what's interesting here is that the argument that's coming in is a function. And we can change that function to actually itself be an extension function on SQLite database. And so this is going to blow your mind, but it's actually a crazy powerful concept. So the function that's being passed in is now an extension function on that object. And so instead of passing in this into the function, that function actually exists on the SQLite database now. And so because we don't really need this, we'll just get rid of it. But the function behaves as if it was defined on SQLite database. And what's great is that if we want to call this delete method, we don't have to qualify it with anything because we are a SQLite database. We can now get rid of that it. And so now every expression that you put inside this block is going to behave as if it was like a private method inside SQLite database. So you don't have to qualify it with anything. It will always execute on the right object. And so this is fantastic. This is what we've turned our code into. But there's still a problem. There's still a huge problem, actually, for Android. And that's the generated code looks like this, which is kind of crazy, but it's not that bad. It's only 5 or 6 lines. But the equivalent in Java code is actually creating a new instance of a function and passing it into our generated static method. And this is kind of unfortunate because before we just had a bunch of lines of code that are executing in order, not really doing any allocation. And if we do this, we have to allocate these tiny little function objects every single time we want to use these extension function expressions. So this is not good. This is going to create, these are the types of objects that just end up causing a lot of GC, these tiny little objects. Thankfully, there's a way to get rid of it in Kotlin. Our function that we have here, we just defined as an extension function. And it takes in this, this function expression, and that's the problem, is that that function expression has to turn into an anonymous class. We can actually take this and turn it into an inline function. We can tell the Kotlin compiler that what I'm doing inside this method, I need it to actually, instead of just calling it as a static method, I need you to actually take my body and replace it in the calling code. And so that generates all this nonsense. But that's great because this is the Java equivalent. And that's the same exact slide that we started with. So the generated class file ends up looking the exact same as if we were compiling this potentially error-prone Java code. It's exactly the same. So rule of thumb, extension function expressions plus an inline function equals the exact same equivalent as the Java code. And so now we can clean up any API that we want. Pick your worst API in Android. There's certainly no shortage. There's a lot that are transaction-based, so we could reuse the same pattern for fragments or for shared preferences, or just anything that annoys you and you feel like you're writing too much code. So I just picked kind of one at random. Notification builders, you end up, they're not too bad, but we could clean it up a tiny bit. And so just find some API that has a lot of, this one's actually doesn't have a lot of ceremony, but there are a lot of APIs where you just have to do certain operations in order, or you have to remember to put that inside the try block or outside the try block, or not in a synchronized block, or there's tons of these examples. And so this is a great way to add functionality to these types with no overhead in the actual generated code. And so the JetBrains people kind of have taken this to a ridiculous extreme and created this library called Anko. And it's really clever. It's basically, the idea is that XML is very declarative. And it's actually perfect for UI because it's hierarchical. And UIs are inherently hierarchical when you're building them up. But with these extension function expressions, we can now represent that in code in that same hierarchical way while still having the ability to reference all of the methods and all of the refactoring tools and all of this static analysis of Java code itself for representing UIs. And so these are just a bunch of extension function expressions which are going to generate, create instances of these classes, add them to their parent, set the right properties. And instead of the concepts that we use in XML, like including layouts, you can actually just call a function, call a method that returns this partial layout and compose these things together. So it's certainly an interesting concept. It's definitely not for everyone. They also have a custom preview plugin. So one of the nice things about XML is you get to pre-render the view and see how it mostly would look on a device. And so they've written one for this Java code, so it will statically parse the Kotlin and do that rendering as well. So it's a great example of taking something that annoyed them, which is the XML and the general pain of having these two separate worlds of Java and XML and resources, and combining them into a single source, which is just the Kotlin source file. And so this will actually end up being faster than XML because you eliminate the overhead of parsing the XML and you eliminate the reflection that's incurred when you look up the classes that are defined in XML. So it's not for everyone, but it's definitely a novel solution to a problem that they perceived. And so that's it. I really just wanted to give kind of an introduction to the concepts that are most useful for fixing the problems of Android. There's a ton of other things in the Kotlin language that are just general improvements, but that's for any Java code. And there's these very specific things which allow you to take the problems of Android and potentially remedy them. So the Kotlin website is absolutely fantastic here. There's a ton of resources. There's an interactive editor where you can actually create and run Kotlin code just in your browser. And they have a series of interactive tutorials that you can step through that will teach you the syntax in that same editor. And so, yeah, that's all I have. I just wanted to point out that Kotlin is just hit its first beta 2 days ago, I think. So the final 1.0 language is about to be released here in hopefully a few weeks. They're targeting by the end of the year. So a lot of people have been holding off because it's a pre-1.0 language. So that argument for not using it is about to disappear. And so I encourage you all to go out and experiment with it. And thanks for coming.